This lecture is going to deal with acids and bases, and if you recall, acids and bases are one of our three main types of chemical reactions. We've previously talked about ionic precipitations. Later we'll talk about oxidation reduction, so this one will deal with acid-base reactions. And when we think of acids and bases in this class for now, we're going to look at the Bronsted-Lowry definition of an acid and a base. And so this definition of a base deals with the movement of a proton, or an H plus. Right, so hydrogen has one proton and one electron. So if you remove the electron to just have the cation hydrogen, this is the same as a proton. So our definitions then would be an acid, and the Bronsted-Lowry definition would be a proton donor, an H plus donor. So this is the molecule that's going to lose the H plus. And then the base is going to be the molecule that's going to gain that H plus. So let's look at a couple of examples. In our first simplest example, if we just take our H plus cation and react it with our hydroxide anion, these will react to form water, as shown by this chemical reaction. And so our acid would be H plus, and our base would be hydroxide to form water. Another example would be that of hydrochloric acid, HCl, plus water goes to form the hydronium H3O plus cation and chloride. If we look at this chemical reaction again, we can identify the acid and the base. So the acid will be the molecule that donates an H plus. So we see that HCl is the acid, and the base is water, right? So water is grabbing the H plus from the HCl. And in general, when we have an acid reacting with water, we are going to form the H3O plus hydronium ion. And the more acidic our acid, the more hydronium will be in solution. The other thing we can take note of during this reaction, I've drawn this out in Lewis structures intentionally so that you can see that the H in HCl gets transferred to the water, but the two electrons in the covalent bond between hydrogen and chlorine remain behind with the chloride anion. So here would be another example of an acid-base reaction. We have NH3 ammonia reacting with water to form NH4 plus and hydroxide. And so when we look at this reaction, again highlighted in red is the hydrogen, the H plus that moves, and we can see that ammonia is going to accept the H plus from water to form the ammonium cation and the hydroxide anion. So we can see in this case ammonia is our base and water is our acid. And since we're dealing with a base reacting with water, we can say that the stronger the base, the more hydroxide is present in solution. The other thing to take note of both of these past two reactions we looked at is the formation of ions in solution, in this case ammonium and hydroxide. And so we should be able to predict that these would conduct electricity because of the formation of ions in solution. So as we move through chemistry, one of our goals is to be able to predict reactivity based on structure. And so we should have a sense of what types of molecules will be acidic, what are going to be acids, and what are going to be bases based on their molecular structure. And with respect to acids, we can come up with two main classes of compounds we should predict to be acids. So the first are compounds where the acid is bound directly to a highly electronegative element. So what we mean by that, as shown here, is when you have a hydrogen that's covalently bonded to an element that is very electronegative. So typically a halogen. So HCl, HBr, HI, and HF, these will be acidic, and this is due to the greater electronegativity pull of the halogen, removing electrons from that proton, making it easier to break that chemical bond. As a reminder, when we name acids, we're going to name them by starting with the prefix hydro, and we're going to add the suffix ic, acid, to the end. So HCl would be hydrochloric acid, HBr would be hydrobromic acid. The second major class of acids we should be able to identify would be those where we have the hydrogen bonded to an oxygen that is in turn bonded to a central atom that has a double bonded oxygen to it. And so when you look at this, look at these structures of acetic acid and nitric acid. The red hydrogen is acidic because it's bound to an oxygen, and that oxygen is bound to an atom that has a double bond to a different oxygen onto it. And again, we can think about this from an electronegativity difference. That double bonded oxygen pulls electron density from the carbon or nitrogen, which in turn is going to pull electron density away from that OH group and really weaken that OH bond. With bases, so if bases are going to accept a proton, one of the things they have to have is a lone pair of electrons, because it's really that pair of electrons that's going to grab the H+. So we can think about two major types of bases, and the first is metal hydroxides. So metal hydroxides are bases because these are ionic compounds with the hydroxide anion, and if we put these in solution, they will dissociate to some extent, directly releasing hydroxide. And recall that we said the stronger the base, the more hydroxide present in solution. So an example would this be something like magnesium hydroxide will often dissolve in water to form magnesium 2+ and 2 hydroxide anions. The second type of base that we should be on the lookout for in this class are ammonia and similar compounds. So ammonia has nitrogen with a lone pair and 3 hydrogens attached. This can act as a base. So the similar compounds would be a nitrogen with a lone pair and 3 things attached. That nitrogen will be basic, meaning it will be able to grab a proton from water or an acid and react in an acid-base reaction. Now that we can identify acids and bases, just want to talk for a moment about acid-base neutralization reactions. These are reactions between an acid and a base in which the moles of acid equal the moles of base. So we think about this as a neutralization. If we have a bunch of acid and we want to remove that acid or eliminate that acid, we would have to add base, or vice versa. If we have a bunch of base that we want to neutralize, we could add acid to neutralize it. You see this sometimes with acid spills or base spills in terms of cleanup. So in the reaction we've shown here, we have something like hydrochloric acid, HCl, reacting with potassium hydroxide. So we have our acid and base. And when we look at this, we see the hydroxide will be our base and accept the proton from HCl, forming our H2O, water, and our KCl, ionic salt. And one of the things to notice is anytime we have this reaction between this neutralization between a strong acid and a strong base, such as HCl and KOH, the products of this are always going to be water and a salt. Right? So it's water and it's whatever counter ions were there. So just like with an ionic precipitation reaction, we could break down the reaction further and work towards the net ionic equation. We can do the same thing here. And we could write first the ionic equation by separating everything that says aqueous into its ions. And so in solution, really, this would be H plus aqueous plus our Cl minus aqueous plus K plus aqueous plus hydroxide aqueous goes to water as a liquid plus the potassium ion aqueous and the chloride ion aqueous. Then we can remove our spectator ions, which are all the potassiums and chlorides present. And what we'll be left with is our net ionic equation for an acid-base neutralization reaction is simply H plus OH minus goes to water, right where we started as we started our discussion of acids and bases. Thank you.